Welcome back to the Deep Dive.
Great to be here.
Today, we are getting into something absolutely fundamental. I mean, it's the organizational chart for chemistry, right? The periodic table of elements.
It really is hard to imagine chemistry without it.
But we're not just, looking at the poster on the wall. We want to dig into how it actually came to be. That whole messy 19th century scramble to make sense of the elements.
Yeah, messy is a good word for it.
So our mission today, for you listening, is to sort of cut through that timeline. We want to pull out the key moments, the breakthroughs, maybe some surprises, and really understand the people who turned this elemental chaos into the predictive tool we have now.
And it's important to get this up front. It wasn't this smooth, linear path, not at all.
Right.
The table we know today, it's built on, well, almost a century of trial and error, some ideas that worked partially, others that didn't, and definitely some serious competition between scientists.
Rivalries even.
Oh, yeah. Sometimes it really came down to who published first or who was willing to, stick their neck out with a bold prediction.
Okay, let's trace that journey. Where does it even begin? We're talking early 1800s.
That's right, early 19th century. And back then, really the only quantitative thing they could consistently measure for elements was their relative atomic weight.
So mass was the starting point. But how do you go from just a list of weights to seeing patterns? That seems like the first big leap.
It was. And that first real spark, that initial pattern recognition, we usually credit that to Johann Dobereiner in Germany.
Dobereiner, okay.
He was working around, 1817, but his main publication on this was closer to 1829. And what he found wasn't some grand system for everything, but a really neat mathematical observation within small groups of elements.
These are the triads, right? Groups of three.
Exactly, the law of triads. He noticed that certain groups of three elements didn't just have similar chemical behaviors, which people kind of already knew, but their atomic weights had a specific relationship.
Okay, so what was the relationship?
Take calcium, strontium, and barium. They all act kind of similarly chemically. Dobereiner showed that if you take the atomic weight of calcium and the atomic weight of barium, the average of those two numbers is almost exactly the atomic weight of strontium, the element in the middle.
Wow. Okay, so it's a numerical link, not just a vague similarity.
Precisely. It was the first time someone demonstrated that chemical properties were tied to a number, to a mathematical pattern in the weights. He found other triads, too, like the alkali metals, lithium, sodium, potassium that worked.
On the halogen.
And the halogens, yes, chlorine, bromine, iodine, same pattern. It suggested some kind of underlying order.
That feels huge, just establishing that principle that there's math behind the chemistry. But okay, groups of three is one thing. How do you get from there to organizing all the known elements? That must have been the next challenge.
A big challenge. And the next significant step came, well, a few decades later, mid-1860s, with an Englishman named John Newlands. Yeah, he took Dobereiner's basic idea of a numerical progression and pushed it much further. He really introduced the concept of periodicity, the idea that properties repeat in regular cycles as you go up in atomic weight.
And this is where we get that famous, slightly weird analogy, right? The law of octaves.
That's the one. It definitely sticks with you. Newlands arranged the 56 elements known at the time in order of increasing atomic weight, and he noticed that properties seemed to repeat every eighth element.
Like a musical scale.
Exactly like a musical scale. He literally drew the analogy to the 7 intervals of music. You start on do, you go up 7 notes, and the 8th note is do again, an octave higher. And it sounds similar. He proposed elements work the same way. Element 8 was like a chemical octave of element 1.
That sounds quite elegant in a way. But I can imagine the scientific community back then maybe wasn't thrilled about comparing elements to music notes.
You imagine correctly. Some members of the Chemical Society in London actually mocked him for it. They thought the analogy was, well, unscientific, maybe a bit silly.
Okay, so ridicule was part of it. But were there actual scientific problems with his system, too?
Oh, definitely. That was the bigger issue. The law of octaves actually worked reasonably well for the first couple of octaves, for the lighter elements up to about calcium.
But then
it started to break down. As he got into the heavier elements, the strict 8-element periodicity just didn't hold up anymore.
Why not? What went wrong?
Well, a couple of things. He was still relying purely on atomic weight, which, as we'll see, isn't perfect. But critically, he also kind of assumed all the elements had been discovered.
No gaps.
No gaps. So when the pattern didn't fit, he sometimes had to force things like he put 2 elements in the same box to keep the rhythm going, or elements ended up in columns where their properties clearly didn't match the others in that column.
So the underlying idea of periodicity was there, But the execution, based only on weight and assuming a complete set of elements, was flawed.
Exactly. It was an important conceptual step recognizing periodicity, but his specific model didn't quite work, and it didn't gain widespread acceptance.
Okay, so Dobereiner finds a numerical link in small groups. Newlands introduces periodicity, but it's flawed. This sets the stage, then, for the late 1860s, which sounds like the real turning point. And the big names here are Mendeleev and Meyer.
Dmitry Mendeleev in Russia and Lothar Meyer in Germany. And yeah, the late 1860s is absolutely when the periodic table, as we start to recognize it, really takes shape.
And their work was happening kind of at the same time, wasn't it? Almost independently.
It was remarkably parallel. It's actually quite striking. Both were working on organizing elements by atomic weight. Both recognized the periodic recurrence of properties, and both came up with very similar table arrangements. Meyer even drafted a version of his table in 1868.
Okay, so if Meyer had a table in 68, why is Mendeleev the name everyone remembers? Why does he usually get the main credit for the periodic table?
That really comes down to one key difference: prediction. Mendeleev published his first version of the table in Russia in 1869. But he didn't just arrange the elements that were known. He did something much bolder. He looked at the problems in earlier systems, like Newlands, where things didn't quite fit.
The gaps in the misalignments?
Exactly. And instead of seeing them as failures of the system, he saw them as predictions of the system. He intentionally left empty spaces in his table.
He didn't just ignore the gaps, he highlighted them.
He highlighted them and he said, basically, there's an element missing here. It hasn't been discovered yet, but when it is, it will have these specific properties.
Wow, not just something goes here, but here's what it will be like.
Precisely. He famously predicted the properties of 3 elements in particular, calling them Eka aluminum, Eka boron, and Eka silicon. Eka meaning one or first step away in Sanskrit.
And he predicted more than just their atomic weight.
Oh yeah. He predicted their approximate atomic weight, sure, but also things like their density, their melting point, what kind of oxides and chlorides they would form, how they'd react, really specific chemical and physical properties.
How could he possibly do that for something no one had ever seen?
Well, it wasn't just guesswork. It was based on the logic of his table. He looked at the properties of the elements around the gap, the ones above, below, and to the sides. By interpolating, kind of averaging or reasoning from the known properties of the neighbors, he could make very educated predictions about the properties the missing element must have to fit the periodic trend.
That's incredible. It turns the table from just a classification into a predictive machine.
That's exactly what it did, and the confirmation came relatively quickly.
When those elements were actually found.
Yes. Within about 15 years, chemists discovered gallium, scandium, and germanium. And guess what?
They matched his predictions.
They matched Eka aluminum, Eka boron, and Eka silicon remarkably well. Gallium fit Eka aluminum, scandium fit Eka boron, germanium fit Eka silicon. That predictive success was stunning. It basically proved the fundamental validity of his periodic law.
Okay, I can see why that sealed his reputation. What about Meyer, then? The other guy.
Lothar Meyer. Well, his work was excellent, very similar insights about periodicity, and he even plotted atomic volume against atomic weight, showing these clear periodic peaks and valleys. His 1868 draft table was very close to Mendeleev's, but he didn't publish his full detailed paper laying out his table until 1870.
After Mendel.
After Mendeleev's 1869 paper. And crucially, while Meyer certainly recognized the patterns, he didn't make those same bold, specific, quantitative predictions about undiscovered elements that Mendeleev did.
So it was partly timing and partly the lack of those killer predictions.
Pretty much. There's even a story that Meyer had given his paper to a colleague for review before publishing, which caused a delay. Whether that's the whole reason or not, Mendeleev got his work out first and, critically, included the predictions. In the scientific world, especially then, predicting something unknown and being proven right, that carries enormous weight.
So while there's maybe still some debate about who was truly first in concept, Mendeleev's predictive power really cemented his place.
It's generally how it's viewed, yes. Though Meyer's contributions were definitely significant.
Okay, so Mendeleev, building on the earlier work, creates this powerful predictive table based on atomic weight. But you hinted earlier that atomic weight itself wasn't the perfect organizing principle. There were still some glitches.
There were. Tiny ones, but persistent ones. Relying solely on atomic weight occasionally led to elements being placed slightly out of order in terms of their chemical properties.
How so?
Well, take tellurium and iodine. If you order them strictly by atomic weight, tellurium comes after iodine. But chemically, iodine clearly belongs with the halogens, like chlorine and bromine, which are in the column before tellurium's group. Mendeleev actually swapped them in his table, trusting chemical properties over strict weight order, but it showed weight wasn't the ultimate answer.
And the reason for that mismatch has to do with something they didn't know about yet.
Exactly. It has to do with isotopes, atoms of the same element that have slightly different numbers of neutrons and therefore different atomic weights. The chemical identity isn't set by the weight, but by something deeper.
Which leads us to the 20th century and the modern understanding.
Right. The big shift comes with the discovery of atomic structure, protons, neutrons, electrons, and the realization that the truly fundamental property defining an element isn't its mass, but its atomic number.
The number of protons in the nucleus.
That's the one. The number of protons determines the number of electrons, and the electron arrangement dictates the chemical behavior. It's a perfect organizing principle. There are no exceptions, no need to swap pairs like tellurium and iodine. When you order by atomic number, everything falls into place chemically.
So the modern periodic law isn't based on weight, it's based on number. Properties are periodic functions of atomic number.
Precisely. That fixes all the little anomalies from the weight-based tables.
And who really drove that modern view and shaped the table into the format we see absolutely everywhere today?
For the modern structure and layout, a huge amount of credit goes to Glenn Seaborg, an American chemist working mainly in the mid-20th century.
Seaborg. Okay, what were his key contributions?
Well, first, Seaborg was instrumental in discovering many of the transuranic elements, the really heavy elements beyond uranium, number 92. These are mostly synthetic, made in labs.
Right, the ones at the very bottom, often.
Exactly. And the problem was, as these new heavy elements were being discovered, scientists were trying to kind of shoehorn them into the main body of the existing periodic table, and it was making a mess. The properties didn't quite fit the columns they were being put into.
It wasn't working.
It wasn't working well. Seaborg had a major insight. He recognized that these elements, starting with actinium, element 89, formed a whole new series, similar to the lanthanide series that starts earlier in the table. He proposed pulling both these series out of the main body.
The lanthanides and these new ones, the actinides.
Yes, he suggested placing the lanthanides and the actinides as two separate rows below the main table. This did two things. It acknowledged their unique electronic structures. They fill 4 orbitals, which is different from the main groups, and it kept the main body of the table nice and tidy, reflecting the d-block transition metals correctly.
Ah, so that's why we have those 2 rows floating at the bottom. It was Seaborg's structural idea to make the overall pattern clearer.
That's right. It gives us the familiar shape of the periodic table we all recognize from classrooms and textbooks. It was a really crucial structural change based on a deeper understanding of electron configurations and the nature of these heavy elements he helped discover.
And they even named an element after him, right? Seaborgium?
Element 106, yes. A fitting tribute to his huge impact on understanding the heaviest elements and organizing the modern table.
Okay, so let's quickly recap this journey for everyone. We started with Dobereiner seeing numerical links in triads.
Right, a first hint of math.
Then Newlands introduced periodicity with his musical law of octaves, flawed but conceptually important.
Pointing towards repeating patterns.
And then the big leap with Mendeleev and also Meyer, organizing by weight, but crucially, Mendeleev predicting unknown elements based on gaps.
Prediction was key. That really validated the whole idea.
Then the shift in the 20th century from atomic weight to the perfect organizer, atomic number.
It's in the glitches.
And finally, Seaborg giving us the modern layout by pulling out the lanthanides and actinides, accommodating his own discoveries of heavy elements.
Leading to the structure we use today.
It's an amazing story of incremental discovery, insight, and correction over, what, nearly 150 years?
Absolutely. Built piece by piece.
All right, before we wrap up, we always like to leave you, the listener, with something to chew on, a final thought based on what we've discussed.
Yeah, so thinking about this whole process, especially those very early steps, consider this. The entire framework of modern chemistry rests on this table, on recognizing